This podcast is sponsored by QCon AI, the Applied AI conference for software developers. Focusing on the practices of artificial intelligence and machine learning, QCon AI takes a different tack than most other major software conferences in the AI ML space today. Rather than focusing on data scientists, QCon AI targets how full stack software engineers can apply machine learning and AI techniques in their day-to-day roles. QCon AI takes place in San Francisco, April 9th through 11th, 2018. You can find out more about the conference online at qcon.ai. I'm Wes Reisz, and I'm the chair of the upcoming QCon San Francisco that will be held in the Bay Area November 7th through 9th. Today's podcast was recorded just before QCon New York this past June and features a very well-known machine learning researcher, John Langford. Dr. Langford is a machine learning research scientist and principal contributor to Vowpal Wabbit. Think Elmer Fudd when you hear that. He is currently working at Microsoft Research in New York and was previously affiliated with Yahoo Research, Toyota Technical Institute, and IBM's Watson Research Center. John earned his PhD from Carnegie Mellon in 2002. He is a preeminent thought leader in the ML space. Additionally, he serves as the chair of the International Conference on Machine Learning in New York that was held just after QCon New York on June 19th through 20th. He is the person you want to talk to catch up on the ML space. John, thank you for taking time out of your schedule to join us, and welcome to the InfoQ podcast.
Thanks.
Let's start off with just a basic question. What is your role and function?
So primarily I'm a researcher, but I'm kind of guiding the development of at least two different systems. One of them is VW, Vowpal Wabbit, which is an online out-of-core learning system. So that's particularly useful when you have very large data sets or when you want to kind of learn in an interactive loop. And it's also very good at handling the framing of problems, much better than many other platforms.
Let's talk about Vowpal Wabbit. How is Vowpal Wabbit different than some of the other machine learning packages we might be familiar with?
So many people try to create sort of a machine learning toolkit, which has all machine learning algorithms. VW is not like that. Its goals are rather different. The goals are partly about incorporating latest research into algorithms, and partly about creating a very efficient and fast and easy-to-use learning system.
When you say incorporate some of the latest algorithms from machine learning, can you give me some examples, some context?
Yeah, so a recent patch that we just put in was for logarithmic time classification. If you want to predict one of k things, that can become very burdensome computationally when k becomes large. So you'd rather not have an order k approach, you'd rather have an order log k approach. So there's a recall tree algorithm that is about to go into VW, right? And that takes time logarithmic in k.
So I've heard you also describe it as fast learning. What do you mean by fast learning?
Yeah, so there's an example of kind of machine learning malpractice that I've run into a number of times. So somebody comes up to you and they say, hey, I have a big data learning problem, and I'm using Hadoop, and it's working really slow. And you ask them, what are they doing, and how much data do they have? And they say, I have about 100 megabytes of data, and I'm using naive Bayes in Hadoop. And at that point, you kind of want to cry, because VW can swallow 100 megabytes of data in less than a second of time. And the default learning algorithm is linear, which is typically more powerful than naive Bayes. So you can get a better result in less than a second on a single machine. So VW basically is unlocked as far as the amount of data you can put in. It operates out of core, and it does this with kind of an assembly line of operations that are done on examples, leading to a very fast parsing and utilization of the examples as it's being observed.
So at QCon New York, your talk is going to focus on VW, right?
Partly it'll be on VW, and partly it'll be on this new decision service that we're working on. It's about half and half between the two.
So is it going to go into the system, or are you going to do examples? What's the focus going to be?
So I'm going to give some overview of what VW can do. There's not really time to dive into everything because there's too many different things. So we'll go into details on a few things, and I'll give some examples about showing how it works.
think the example, what was the example you were going to go through? It was a decision service for personalized news and recommendation. Is that right?
Yeah. So VW is used inside of the decision service, which is a more complete system that supports a full data lifecycle. It's been deployed for personalization of news in MSN, and they've been very happy with that. It gave them about 25% or so click lift.
I got to ask you, we've talked about this before, and everyone's always going to wonder. Can you tell me a bit about the name?
Yeah, the name comes from several different references. One of them is, as you said, Elmer Fudd, who turns his R's into W's. But if you remove Elmer Fudd, it's Vowpal Wabbit. Vowpal comes from Jabberwocky, which is a poem that has nonsense words that you can understand because of the way they're used. So Vowpal means very sharp. And then I guess what I was thinking about at the time was this Monty Python and Search for the Holy Grail when they run into a particular rabbit. If you go to YouTube and search for Killer Rabbit, you'll find it. It's pretty funny.
Yeah. I think I just tweeted it out today right before QCon New York. All right, so we're going to kind of build up. We're going to kind of start with kind of starting out, then kind of work up to deep learning and some things like that. But I teach a class at the University of Louisville, and I had a student a couple months ago ask me about getting started with machine learning. What advice would you give someone who's just starting out in ML on what to pick up, what to look at, and what tools to kind of adopt?
I think it's good to have kind of a relatively thorough background that you would get from taking a class or two. There's actually a number of classes that are online. One of the first MOOCs was by Andrew Ng. And then there's a Caltech professor who actually taught me machine learning. I'm blanking on his name at the moment. Yasser Abu Mustafa, that was his name. But he also has his classes online. So these between the different classes online that you can find, you can actually get a very good background on machine learning in general. Some of that, I think, should include some learning theory, because what I find is that people who don't get exposed to learning theory tend to make sort of rookie mistakes much more easily. And then as far as getting practical experience, I think Kaggle is actually a pretty good source of practical experience. There's a lot of discussion forums around the competitions that they have to solve prediction tasks. So if you participate, you're guaranteed to be working through the process of doing machine learning. And if you follow the forums, you'll learn how to do things better. So some experience there, I think, can be very effective in helping round out what you might learn in a classroom.
There's a quote that I saw online that you have, and it says ML is shifting from an academic discipline to an industrial tool. Can you expand a bit on that?
Sure. So just observationally, what you see is machine learning is getting used much more in industry than it was a decade ago. When I was starting out in machine learning, I had no idea that it would mushroom to be such a high interest subject. Another way to measure this, though, is just by participation in conferences. So for ICML, which is a very academic conference, a large fraction of the participation is actually from industry. And one way to think about that is there's 4 out of 9 tutorials, I think, which come from industry at ICML. And those are actually the most popular tutorials. And so a lot of the research is now being done in industry, and a lot of and then the application industry is making a huge difference in many settings. I think that for things like search and ads, for example, ad marketplaces, machine learning is so key to things that basically just wouldn't work without machine learning.
So these things all seem to be kind of customer facing. Are there applications of ML that are like inside the data center or internal that you're hearing through ICML or other places?
So I think there's a lot of machine learning for control that you don't necessarily hear that much about because it's not customer facing. So think about like a farm, and now you want to try to predict when you should water or when you should plant or things like this. So people are trying to apply machine learning in these situations and sometimes perhaps getting pretty strong results. But you don't hear about it as much because it's just not the kind of things you hear very much about.
What are some of the big trends you're seeing for ICML this year?
So certainly neural networks are very strong. The neural networks are taking 56 out of 332 accepted papers. And several of the tutorials are about various forms of neural networks. Reinforcement learning is very strong. Optimization is very strong. But even if you take those three strong things, the field is very broad. So that's still only a small minority of everything that's going on.
I see you made reference to it, but I see even at QCon, I see a tremendous amount of academic research applied to industry and just about everything across the board, particularly with distributed systems and a variety of other areas. Why do you think there's like this rediscovery of academic research right now?
That's interesting. So broader than just machine learning.
Yeah, absolutely. I see it across the whole, about everything we're doing. Algorithms, Wesley Reisz, just some of his research is coming back up more and more. And then at QCon London, I think 2 of the 4 keynotes we had had an academic focus.
Yeah. So I think that when you go to distributed systems, the ability to hack what you want based upon just thinking about it a little bit becomes more limited. Certainly debugging distributed systems can become a nightmare. So in machine learning, it's a shift towards sort of a database programming going on. And if you're thinking about database programming, it's actually not that easy to just come up with a field of machine learning on your own. There's quite a bit going on there. So you really want to start thinking about machine learning, and that's just something that was only really in academia 2 decades ago. And it was only barely out of academia a decade ago. For something like distributed systems, well, I think distributed systems have already existed, but I think they've become much more important because people are trying to shift towards cloud-based systems, which are by definition distributed, which means they need to worry about things like reproducibility and locking and race conditions in a sort of unavoidable way that maybe wasn't quite so true when everybody was working with a personal computer. So maybe the concerns that academics have been worrying about for a long time are just becoming more relevant now than they were previously.
Yeah, I think I agree with that. So some of the concerns around ML that I've also seen at QCon that I'd like to chat a bit about, like where's the line between the amount of data that you train with machine learning versus just like response speed? Is there a line, or how do you decide when enough data is enough given as much information as we have now?
Mm-hmm. So there is actually some of the learning theory tells you when you have enough data, but it tends to be if you're working with this specific representation, when do you have enough data so that you don't need more in order to learn with that representation? The real game in machine learning is often about choosing the representation and choosing the features that you feed into your learning algorithm. So in those situations, it can be pretty hard. And I think often what happens is relatively ad hoc. It's something like you work with some data that you have, and then you find the best performing model you can get on that data, and then try to get some more data, and then you see how much that improves things. And at some point, you run out of time or budget or whatever, and then you work with that. That's it. It's hard to say when you have squeezed all the information out that you might hope to get. It might always be there's some new feature that you could bring in that you didn't bring in previously that could make a big difference in the performance that you get. And so it's kind of a question of attention and how much time you can put into things.
So you had I think it was a blog post, an article I read, a ACM blog post, I guess in March, that was referencing the AlphaGo versus Lee Sedol Go match. And just background for people listening, in March there was a match between Lee Sedol, who's one of the top Go players in the world over the last decade, and Go is a 2,500-year-old game that's like just an order of magnitude, or several orders of magnitude higher complexity than chess. Basically, AlphaGo, this algorithm from our AI system from Google, beat Lee Sedol in a match 5 matches 4-1, and it spawned tons and tons of discussions about AI. So I'm curious, what does this this Go match mean for AI and machine learning?
Well, I think it's a great milestone. It's impressive that they've been able to solve this game better than the best human. That's definitely a milestone. I guess I see this as a marker of progress in AI rather than a solution to AI, which I think some people were taking it as.
Yeah, I think your blog post kind of said, well, let's take this with a grain of salt. While it's important, we need to really think about what this means. Can you talk a bit about that? About why you had some reservations?
Well, I mean, the AlphaGo algorithm itself is using a combination of good known techniques to achieve this. The reinforcement learning setting, which the AlphaGo algorithm is solving, is not in general solved by the AlphaGo algorithm. So it's easy to create reinforcement learning algorithms, even natural reinforcement learning algorithms, where the kinds of algorithms used there are going to be very ineffective.
What was the main algorithm that it used?
So it was using Monte Carlo tree search with a deep learning algorithm to compute the values. Monte Carlo tree search has been known to be pretty effective in Go, more effective than you might imagine. So let me just briefly say what Monte Carlo tree search is. When you're trying to solve games conventionally, you're doing some sort of search process where you say, well, if I move here and then the other guy moves there and then I move there, going over and over again, what is the value of the outcome going to be? In Monte Carlo tree search, what happens is instead of doing a search over all of those alternating quantifiers, instead what happens is you randomly pick after the first step or maybe after the second step. So that allows you to roll out things very quickly, and then you just use the average outcome over those random choices to get a value for the overall outcome. So it's kind of a very simplistic algorithm, but it's very fast, which means that it's possible to employ it on computers very effectively. And it also tells you something about Go. It says that Go is more of a territory game, which is exactly what you would say if you start thinking about what Go is doing. So that strategy, using reinforcement learning and using deep learning and using existing game playouts by Go masters, were combined together to create this AlphaGo algorithm.
And so it's more an example of the right algorithm given how Go works than it is, I guess, artificial intelligence deciding how to approach the game. Would that be fair?
Yeah. So there's many other games where Monte Carlo tree search does not work, at least not very effectively at all.
I mean, but this is an example of deep learning, right? I can't talk to any data scientist over the last couple of years and not hear how deep learning is one of the next big disruptions right now in the ML space.
So I think deep learning is a disruption which has already happened, and it's been pretty amazing to watch. The field of vision and the field of speech have been completely turned over by deep learning. Right? So there's this ImageNet competition year to year, and it's about 2012, I think, when the first deep learning-based system won a competition there, and it won by a lot. And the systems have continued to improve radically. The last one was this ResNet, which had 152 layers. It's pretty impressive. And it actually reduced the error rate to something similar to the error rate that humans have when they're labeling images. So that's amazing. It means that computers can actually understand what's in an image about as well as a human can, at least in some somewhat contrived but still very interesting scenario. Again, I think this is it's something that's already happened. You're asking about the future as well. I expect there will be new applications of deep learning coming out, and there'll be new things that we learn about representations, and I think those are important. I also think there are other areas of machine learning which are very important. So I think that dealing with causality properly, for example, is very important. Reinforcement learning is related to this. Contextual bandits, this decision service that I'll be talking about, are all related to this. I think that there's also a question of a lot of these algorithms require a lot of TLC. Deep learning is not something that you want to be doing if, as a dabbling. You want to be doing it more as a constantly trying to, you want to have a GPU farm with 100 GPUs. You want to be have a group of people who are thinking about ways to try to improve things. It's not a simple thing to get to the state of the art with. You want learning algorithms that just work, right? And it's never going to be the case that everybody knows deep learning. There's some real need to have algorithms that just work. And so reaching that point is surprisingly difficult. There tends to be a lot of hyperparameters or whatever that you tune when you use machine learning. You would like to not have that. You'd like it to just work.
So let's talk about just work for a second. The track you're doing at QCon is called the commoditization of ML. It seems kind of an odd set of words to put together. Are we really at the point where we have machine learning as a commodity? Are we close to having machine learning as a commodity where it can just work?
I think we're close. So there have been systems. So there have been plenty of learning algorithms available in toolkits for well over a decade. Over the last few years, what you see is a lot of systems for deploying machine learning. So there's just to name a few, there's Google has some sort of prediction service, Microsoft has Azure ML, Amazon has some sort of machine learning as a service type thing. So making it easy to use what you learn with a machine learned algorithm, that's very useful. There's a step beyond that you have to go in many cases. So when you're applying machine learning, you're applying it in a regime. You're applying it based upon data. And the question is, how quickly does the data age? Some applications like personalized news, the data ages pretty quickly because news articles change, people's tastes change. There's a natural rapid rate of change. Some things are much more persistent. Like if we were doing personalized medicine, the spectrum of genomes that you want to try to apply personalized medicine to probably doesn't change that fast. But there is some rate of change of these things. And that means that the data is a part of the process. So you need to have a system for collecting the data that you use in order to learn the model that you then deploy. That then helps you collect the data that you use. So there's a cycle there. And nailing down that cycle, I think, is the point at which it can really become a commodity in the sense that you don't need to have a data scientist in order to successfully apply machine learning.
Makes sense. All right, if you like what you hear, look for the video on John's Vowpal Wabbit talk at QCon New York on infoq.com in the upcoming few months. You can also find him at ICML New York, June 19th through 24th. Thanks for joining us, John.
Thanks a lot.